Hey there. Ever wonder how your phone predicts the next word you'll type? Or how scientists decode complex systems like weather patterns or animal behavior? It all starts with sequence prediction, figuring out what comes next in a chain of data. And here's the breakthrough. Big language models, LLMs, aren't just guessing. They're learning hidden patterns in data, like a detective solving a mystery by observing examples. Let's dive into the science behind this. First, let's unpack Hidden Markov Models, HMMs. Think of them as a detective's notebook. You can't see the real story, the hidden state, but you get clues like a suspect's alibi or a footprint. HMMs use these clues to infer the hidden events behind them. For example, if you hear a rustle in the bushes, the hidden state might be squirrel or thief, and the clue is the sound. HMMs are everywhere, from speech recognition to analyzing animal behavior. But here's the catch. They're tricky to train, especially with messy data. Now here's where it gets wild. Researchers discovered that LLMs, like the ones powering your favorite chatbots, can learn HMMs on the fly. This is called in-context learning, ICL. Imagine giving a model a bunch of weather data, and it figures out the hidden patterns without being told how. It's like teaching a kid to solve a puzzle by showing them a few examples, and suddenly they're figuring out the rest. The study tested this by creating fake HMMs, like virtual weather systems with different rules. They tweaked factors like how predictable the system was entropy, and how quickly it forgot past states mixing rate. Then they fed sequences of observations to LLMs, and checked if the models could predict the next clue. And here's the kicker. The LLMs didn't just guess. They converged to near-perfect accuracy, matching the theoretical best possible performance. When the hidden patterns were simple, low entropy, fast mixing, the models nailed it. Even in tricky cases, like highly random systems, they outperformed traditional methods like the Baum-Welch algorithm, or LSTMs. But it's not just theory. The researchers tested this on real-world data, like animal decision-making tasks. Surprisingly, the LLMs performed as well as models designed by human experts. This suggests ICL isn't just a cool trick. It's a powerful tool for uncovering hidden structures in complex data. Let's get technical. The study used Bernstein inequalities to bound prediction errors, ensuring the model's estimates stayed reliable. They also measured performance using Hellinger distance, which quantifies how closely a model's predictions match the true distribution. LSTMs, while strong for long-term dependencies, struggled with high-entropy data. But larger models like QN2, 5-7b adapted better, showing that scale matters. How do these models stack up? HMMs and engrams are fast but limited, while LSTMs tackle complexity at a cost. The key takeaway: the right tool depends on the job, speed versus accuracy, simplicity versus depth. For example, engrams are great for predictive text, but LSTMs excel at translating languages. So what does this mean? It deepens our understanding of how LLMs learn and opens new doors for scientific analysis. Whether it's decoding climate patterns or studying brain activity, this research shows that AI isn't just processing data, it's starting to understand the stories behind it. Want to explore this further? Check the link in the description to see the code and experiments. And if you're curious about how AI learns from examples, hit that subscribe button, because the next video is all about how machines become smarter than we think. Stay curious.